Welcome to our lesson on capacitance in physics. A capacitor is one of the fundamental components in electrical circuits, and understanding how they work is essential in electronics and electrical engineering. So, what exactly is a capacitor? At its simplest, a capacitor consists of two conducting plates separated by an insulating material called a dielectric. The key property of a capacitor is its ability to store electric charge and, consequently, electrical energy. The capacitance of a capacitor is defined as the ratio of the magnitude of the charge on either conductor to the potential difference between the conductors. Mathematically, we express this as C equals Q divided by V, where C is the capacitance measured in farads, Q is the charge in coulombs, and V is the voltage in volts. The most common type of capacitor is the parallel plate capacitor. For a parallel plate capacitor, the capacitance depends on three factors: the area of the plates, the distance between them, and the dielectric material between them. The formula for the capacitance of a parallel plate capacitor is C equals epsilon naught times epsilon r times A divided by D, where epsilon naught is the permittivity of free space, epsilon r is the relative permittivity of the dielectric, A is the area of the plates, and D is the distance between them. Let's examine how each factor affects the capacitance. If we increase the area of the plates, the capacitance increases proportionally. If we increase the distance between the plates, the capacitance decreases. And if we use a dielectric material with a higher relative permittivity, the capacitance increases. A key aspect of capacitors is their ability to store energy. The energy stored in a capacitor is given by E equals 1/2 times C times V squared, where E is the energy in joules, C is the capacitance in farads, and V is the voltage in volts. This means that the energy stored increases with the square of the voltage, making capacitors valuable for applications requiring sudden bursts of energy. Capacitors have numerous applications in electronics and electrical systems. They are used for energy storage in camera flashes and defibrillators. In power supplies, they help filter out voltage fluctuations. In timing circuits, they determine the frequency of oscillations. And in touchscreens, they detect the presence of your finger through changes in capacitance. Capacitors can be connected in series or parallel in circuits, just like resistors. When capacitors are connected in parallel, the total capacitance is the sum of the individual capacitances. C total equals C1 plus C2 plus C3, and so on. When capacitors are connected in series, the reciprocal of the total capacitance equals the sum of the reciprocals of the individual capacitances. 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over C3, and so on. Let's work through a practical example. Suppose we have a parallel plate capacitor with plates of area 0.01 square meters, separated by 0.5 millimeters, with air as the dielectric. Using the formula C equals epsilon naught times epsilon r times A divided by D, and knowing that epsilon naught is 8.85 times 10 to the power of negative 12 farads per meter, and epsilon r for air is approximately 1, we get a capacitance of 177 picofarads. In conclusion, capacitors are fundamental components in electrical circuits that store electric charge and energy. Their capacitance depends on the physical dimensions of the plates and the properties of the dielectric material between them. Thanks for watching this video on capacitance physics. I hope this has given you a clear understanding of how capacitors work and their importance in electronic systems.